Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. So that's textbook. It's a textbook theory called inflation. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky, because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever, and it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, and then it slows down and stops in little patches, and each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse. This is the picture that Hubble took, and you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty, it's got lots of structure, lots of points of light in. There are actually over 10,000 points of light or blobs in that image. Virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now those galaxies on average have 100,000 million stars like our sun in them, at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object is 13.2 thousand million light years away. If civilizations are common, or even slightly common, then there should be civilizations ahead of us.
Yes.
Because there's been so much time. We've had science for, let's say, since Newton or Copernicus, 500 years at most. And look what we've done. We've gone beyond the solar system with Voyager. We've walked on the moon. We're about to go to Mars, I would think. So we're about to begin colonizing our own solar system. We've done that in 500 years. So imagine a million years in the future. It's one of the arguments often used to say there aren't any civilizations out there in the galaxy. It's called the Fermi paradox. Because if you imagine a civilization that's a million years ahead of us, they should have written their presence across the sky by now. You should see them. I mean, you'll see us. If we survive a million years into the future, we will be exploring the galaxy. We will have spacecraft that are going to other stars. We will be doing it. So our signature will become visible, I'm sure, if we last. Of Einstein's theory of relativity, from the external perspective, there is a central problem, though, which is still not solved, which is what lies at the centre of a black hole. You might think of it as an infinitely dense point to which this massive star collapses. So what are we picturing? It's this thing called a singularity. Actually, it's not right to talk about the centre of a black hole, really. Just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that space and time are so distorted that in some sense their roles swap. The singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. But the nature of that thing was not, and is still not, understood. Back in 1905, Einstein realised that space and time are not separate, but they're woven together into something that's often called the fabric of the universe, or more technically space-time. But we now suspect, or at least we have a theory, that space-time emerges from something deeper, which is just basically quantum entanglement. So we think that there is a description of our universe which is just bits of information, basically, or qubits to be more technical, that are entangled together into some sort of network, so space and time don't exist in that network, and then space and time emerge from that deeper theory. This is cutting-edge physics, but it's one of the pictures that we have for what space and time might be. Light doesn't travel particularly fast over cosmological distances, 186,000 miles a second. That means that as you look out to even nearby objects, let's say the closest object you can see with the naked eye, the Andromeda Galaxy, if you look at that, it's about 2 million light years away, it means you see it as it was 2 million years in the past. You look at more distant galaxies, 10 million light years away, 10 million years in the past, and so on. So you could ask the question, well, in that case, are there objects that are so distant that the light travelling from them began its journey close to the Big Bang itself? Is that possible? And the answer is yes. And that light was first detected in the 1960s. It's called the cosmic microwave background radiation. So essentially the idea is, how far can I look in every direction? You can look about 13.8 billion years into the past, back to the origin of the universe.
All the particles in the universe need to be held together by something, and this is the glue, if you will, that's holding everything together.
You get mass, so these particles are solid because they're interacting with this stuff, except for light, which isn't, which travels at the speed of light because it doesn't interact with it.
I have read about the Higgs particle, and I'll be honest, I don't understand what it is. Can you give us a sort of layman's explanation of what the Higgs particle is?
It's the most beautiful, ridiculous story. The prediction, which dates back to the 1960s, is that sometime after the universe got to the size of a melon, and remember the universe today has got 350 billion galaxies in it, each with 100 billion stars.
Yes.
Once upon a time it was the size of a melon. Some point after that it was expanding and cooling, and something crystallized or condensed out into empty space, almost like maple syrup or something. The universe gets filled with this stuff as it cools. And today, now, we are massive, we are solid, because our particles are interacting with that cosmic treacle, or whatever you want to call it.
So
extensions of that, called eternal inflation, say or suggest that maybe that collapse at the end of inflation, maybe it doesn't all stop at once. So you're to picture patches of this rapidly expanding space that are sort of collapsing and making big bangs, which make universes. And so the process is called eternal inflation, because for all we know, it could have been going on forever in a sense, and would be going on now if that was correct. So we would just be a bubble in this sea, an infinite sea of universes, of which we're a single bubble, and that's called the inflationary multiverse. Astronomers have pointed radio telescopes up at the stars for a while, 50 years or more now. We've seen no evidence of any civilizations out there beyond Earth, and that's a surprise. There's a reasonably plausible explanation for that, which is biology, which is that if you look at the history of life on Earth, then you see that life began pretty much as soon as it could here on Earth. We have evidence there was life 3.8 billion years ago, something like that, and the Earth's 4.5 billion years old, so pretty quick in geological time you get life. But then if you talk about advanced life, complex life, multicellular life, then there's no evidence at all back beyond a billion years. Actually, really, in the fossil record, 650 million years ago or something, you start seeing the first evidence of complex creatures. So that means that on this planet, it took over 3 billion years to go from single cell life to anything more complex than a single cell. And then another 500 million years or so to go from the multicellular things to a civilization. So it's 3.5 to 4 billion years. It's a third of the age of the universe. We know that the dinosaurs, other than the birds, were wiped out by a big asteroid impact 65 million years ago. We know that. So occasionally big pieces of rock hit the Earth, and occasionally those big pieces of rock are big enough to cause mass devastation that easily take out a city, pretty easily take out a country, sometimes take out, like the one that took out the dinosaurs, take out pretty much every big living thing on the planet. That's happened before, and it will happen again. What we do now is we look for them quite sensibly, So we map the orbits of as the big asteroids. We've got most of them, we think, that cross the Earth's orbit, and we monitor them all the time. And we have what's called a keyhole system, and it says that if one of these asteroids goes through this point in space at this time, then we're worried about it, and we'll be very careful and we'll watch it. So we're watching them, and if one goes through the keyhole, then what you need to do is nudge it a bit so it doesn't hit the Earth. And the DART mission was the first mission designed to make sure that if we really want to hit an asteroid with something, then we can do it. And it's hard. And so we did it. It was a very clever mission because it's a double asteroid system. So the little one, that one of them was hit, so there's two of them going around each other, and we hit one of them, and that means that you can measure the orbit afterwards of these two things orbiting around each other to see how much we deflected it. So it's a smart thing to do. So we're really developing the technology so that if we have to hit a big one and move it away, then we can do that. And Carl Sagan, he said correctly, if the dinosaurs had had a space program, they'd still be around. And that's basically the DART mission. That's what he's doing. There are bigger, there are things we couldn't do anything about. Comets are really